All right, okay. So when I was asked to give this lecture, when I'm down at the Energy Institute, I have the privilege of sitting in Professor Fludis's office, and he does have a very nice couch. So I think it shows you, if, you know, Fludis was clearly a great man, and the fact that he keep his office there, but they allow people like me to use it is a privilege. But if you go outside his office, this is what you see, okay? And when I was thinking about what to talk about, does this laser pointer work? Yeah. See here on this is here, this is here. So I looked at this document. This document is slightly different because there's a small change in it. But if you look at that, all the people on that, they're mathematicians, scientists, engineers, economists, and lawyers. And it's to the point that Stratus has made many times here. This is really about a multidisciplinary type of activity. So I thought to myself, particularly Elizabeth there, Elizabeth was supposed to give this talk, and I'm giving her place, so to speak. But I met Elizabeth about 6 or 7 years ago to do with the Energy System Integrator, or this organization that I founded, IIESI and ESIG. They're two organizations that I was involved in founding. And this is just a slide from about 6 years ago, so I didn't alter it in any way. And this slide shows you that the energy system, from the customer to the city to the region, is a spatial sort of dimension. And then on the right-hand side, it's electricity, thermal fuels, they start to interact. And then you also have water, data, and transport. And I think, where's Rabbi or Rabbi? Where's he, Mukhtar? I was talking to him yesterday about the water. Yeah. So me and him were discussing the water energy interface, and you can see it here clearly and all the rest of it. And the thing about it is that the energy system integration, it's about optimization, it's about cost and environmental impacts, and at the interfaces is where they couple, is where the interesting stuff goes on. And I think at the end of the day, the control variables are technical, economic, regulatory, anthropological. They're all, the control variables are not just purely engineering. They're everything, okay? And so that's the sort of thought that I started with. And that's where I came up with the title. Because if I'm standing in a room, you know, as an electrical engineer, and I have, you know, I have Rabbi there, and I have Costas, and I have various other people with different disciplines. We all have our own strengths, but, you know, while I might know a little bit about chemical engineering, I don't know a lot, you know, so we all have to sort of accept that in this, we might have some core expertise, and then as we go further away from it, we become less expertise. And that's the sort of the theme of the entire talk. So I'll talk about what I should know. It'd be very egotistical for say I do know it, so I'll say I should know it. And anyone who knows me knows that I'm pretty egotistical, so this was difficult for me to write. So there's things I should know. So I'll explain from my own perspective about this energy transition or energy change. I mean, who accepts the energy system is changing, correct? Is there anyone who doesn't? Right. I mean, I think it's a given. So I'll do it from my point of view. My interest has always been I'm an electrical power engineer, so electricity is my baby. And then renewables was the big thing recently, and that has brought many challenges. And all those fellowships and National Academy memberships have all come about because of my work in how to get renewables onto the grid. And that's my speciality, so to speak. So I'll talk a little bit about them, but then I'll link it directly to sort of the broader energy field. And this is true what I think I know about energy systems integration. And this is where I need a little help from my friends, because I mean, I know the first law of thermodynamics. I sort of know the second. I don't know the third. You know, I'm sort of at a bit of a loss. But, you know, there's people in the room who know it very well. And then things that I don't know, clearly. But I do have an opinion like everyone else in the world. And that's dangerous, because I think Ryan said it earlier on, you know, that we're making decisions based on, I don't know if he quite said bullshit, but I think that's what he meant. But, you know, so that's the problem, is that people are making decisions on the basis. So what I don't know are things that anyone, you don't have to be a Hagler fellow, you don't have to be a National Academy member to have opinions. Everyone has opinions on these things. Does anyone know the picture on the right? Yes, sir. Answer. What is it? Yeah. The Banshees of Inisherin. It's a very famous Irish movie recently. I recommend you watch it. It is the most hilarious and dark movie you'll ever see. Okay, so just some context then. I think this is pretty simple. You know, the EIA, the Energy Information, it's a US organization. It's the Energy Information Administration, yeah. So I just went to that, I just Googled it very quickly, and you can see the US power grid added 20.2 gigawatts of generation capacity in the first half of 2024, and it does an extrapolation for the rest of the year. I'm sure I could have got the most up to date. They probably, in January, they probably update it, so it's extrapolation, but it's clear. In capacity terms, it's mainly solar and wind. and then batteries. And there's very little gas. So there's a big boom in renewables and batteries. That's what's happening on the ground. I then just arbitrarily went back in history. I mean, that 1 year doesn't make a trend, but it is a trend. If you go back to 2020, I just arbitrarily went back to 2021, 4 years ago, Googled something, got this from some source, and you can see there 28 gigawatts of new generation capacity added, and it was completely led by wind. So wind and solar have changed places. So that's definitely a change, but from a technical point of view, it's virtually the same thing in terms of the technical challenges. And interesting enough, in this slide, it shows you that Texas is the lead, okay? And as far as I know, Texas still maintains the lead. Texas has more renewables going onto it than any other state in the US, and leads this drive towards more and more renewables that's happening. So just to say why that drive is happening, one of them, there's many reasons for it, but one of them is just pure out and out cost, yeah? This is Lazard's. I like every year I would recommend this as a source. Every year around about this time of year, they come out with an updated version. I think 2 or 3 years ago, they didn't update it. One of the years they just didn't update it. But this is version 17. They do a comprehensive analysis. It's levelized cost of energy. They do comparisons. And I won't dwell on this because it gets quite complicated. And I fully understand that this is not the entire story. I mean, remember, I do integration of renewables, so I know more than nearly anyone else. The fact is, cost is not what this is about. It's about cost and it's the integration, So it's more nuanced, absolutely. But if you look at this, right, what this tells you is that the cheapest megawatt, the cheapest single megawatt, now it might only be 1 megawatt, I'm not saying it's got terawatt hours in it, in the US in 2024 is a wind onshore megawatt. That's what it is. And the next cheapest is a solar one, okay? And interesting enough, if you look at these, you can look at these slides later. Is this slide, Jeff, is this working, is it? Hold on. Laser pointer, yeah. You see these numbers here? What they are, they're showing you the operation. It's off, is it? Yeah, so they're showing you the operational costs for nuclear and coal, etc. And what they show you is, in fact, some renewables are cheaper than the operational costs of nuclear and coal. So that shows you that renewables are competitive on a levelized cost basis alone. That's not the whole story. That's one of the drivers behind this. Then to go to Texas, which is where we are right now, this is a nice page fact sheet from Texas. Like I said, Texas is clearly leading the field in terms of penetration levels. There's all sorts of numbers and statistics in there. One that I'll read out. They hit 69.15% electricity from wind in April 2022. And they hit 44.17% of solar in 2022, just from those sources and all the rest of it. And there's various other combinations. And all they're doing is growing. I know I was going to get the queue, this queue, people want to connect. And as far as I know, there's something like 70 gigawatts of wind, solar, and batteries want to connect in Texas in the next couple of years. And currently the system is spec'd around about 100 gigawatts. So it's pretty incredible what's happening. But I hate to tell it to the Texans, you like to be competitive and the biggest in the world. This is also happening in Ireland, Great Britain, Australia, California, Spain, Portugal, Denmark, blah, blah, blah. It's happening in lots of places in the world. And in fact, on the statistics, the technical statistics, Ireland is actually the highest, but I won't go there. I'm not competitive. So then in terms, though, of metrics of success, I mean, you can't just, and again, I think that Ryan's comment was very valid. You can't just, it's not political. It's not, I'd love to do this. You have to actually have some grounding, that whole thing. So I think this statement on the right is, I mean, I use it a lot now. I'm not saying I invented it in any way, but you don't see it said so often, I mean, the fundamental purpose of an electricity grid and energy system is maintain supply and demand balance to some predefined level of reliability at least cost. Now, you can throw all sorts of other things in there. You can value carbon or not value it. It goes on the cost side. You can security supply. You can represent all these. So you can nuance this, but fundamentally that's what it's about. The diagram on the left shows you a sort of a very simple pictorial. It was an invited paper I was asked to write recently. It's just published, the reference at the bottom. I'm sure we're going to make the slides available later. So, and if you think about it, reliability and cost trade off with each other, okay? If you want a more reliable system, it's going to cost you more. It's that simple, okay? And this is a trade-off. And what I've done pictorially here is I've showed you that there is the ideal boundary, this is where, this ideal boundary is where we'd like to be. That's where the engineers and economists are trying to push things. This is to Ryan. That's where you want to be. Yeah. Now you can never be there. It's, you know, it's dynamic. It's always changing, but you want to keep close to it. Okay. And what I'm showing in 1, 2, 3, and 4 is what's going on at the moment. We're evolving. The system is changing. And in this case, it's pretty arbitrarily done. You know, 1 goes to 2. So what's happened there is it's got a little bit more costly, but it maintains reliability. Oh, it goes to 3, then it's starting to get more unreliable and more costly. That's not good. So we do something and push it over to 4. So these are the type of, this epitomizes the type of work that I do. I'm the controller that makes 1 go back to 4, if you know what I mean. That's what I do. Okay. And then obviously there's some level, you know, the acceptable boundary is, you know, if you go outside that, you got a really bad system that's expensive and unreliable, and that's not good. So you try to go around the sort of the green area. So that's the metrics of success. So if you take those metrics of success and you look at them from the point of view of this transition, and from my point of view, again, electricity and renewables, there's a paper published in Joule, I think it was in 2022. Oh, yeah, there it is. I haven't put the date in, sorry, yeah. I think it was 2022. This is a paper that was published by my colleagues at NREL. There's 2 key techno-economic challenges to integration of renewables and going higher and higher. So we wrote this paper, the challenge of achieving 100% renewables. To be very clear about it, I'm one of the people in ESIG and all these organizations that I've led and created who have advocated against coming out with anything to say about 100%. Because to Ryan's point, that's just provocative and it's just meaningless in some ways, yeah? But we felt we had to, because there was a lot of people coming out saying on one side it was impossible and the other side it was simple. So we decided we had to jump into the middle of this and say, getting to 100% is neither impossible nor is it simple. It's somewhere in between. So we decided to walk the thin line between the two. And that's one of the reasons we published this paper. But it falls into 2 categories of problems, right? The inverter challenge, designing reliable inverter-based grids, and the balancing challenge. That's it. That's what it is. Most of the problems that people think about renewables now, of how difficult it is to integrate, are actually solved. They're done. They've been implemented. A lot of people are behind the curve, so to speak. So I'm going to talk about both of them. I'm going to talk about the inverter-based challenge first, but I'm not going to speak too much about it, and you'll see why. So what do I mean by inverter-based resources? So this is NERC. NERC is the North American Reliability Commission or Council or whatever. It's a US regulatory, well, it's not regulatory. It's a US reliability organization that maintains reliability in the US system. So NERC defines it as inverter-based resources, generally BPSs, bulk power systems, connected facilities that have power electronic interfaces. So basically wind, solar, and batteries, which are the majority of the capacity that's been connected, are not connected in the traditional way, which is synchronous machines. They're connected by inverters, which is power electronics. That is a huge change to the power system. And it's a change that, mainly speaking, only electrical engineers really appreciate, okay? It's in our domain, you know? That's what we do. So let's talk about it a little bit. So, you know, and this diagram on the left, I won't go through all the differences, but synchronous machines have been replaced by inverters, okay? And you have all the different characteristics. And, you know, if this was an electrical power engineering talk, this is where I'd go, yeah? I'd go deep into this. But this is you know, I'm trying to give a more general talk. But the consequences of these inverters it spawned all these things that Stratus mentioned at the start. The Global Power System Transformation Consortium, is this global organization that I helped found. Then we have the Unified Consortium. That's a US Department of Energy funded initiative out of NREL on inverters. There's the Leverhulme Trust. I mean, I've got a named chair, the Leverhulme. That was based around the challenges that are inherent because of inverters. And EPICS, this organization that I'm the global director for, is a global between the US, Australia, the UK, and other countries. So largely speaking, those initiatives are around addressing the inverter issue. Not quite, but largely speaking, that's what they're about. So what is the issue? So, I mean, again, you'd have to do Sony. Okay. You'd have to do a sort of a 101 in electrical engineering and build up from there. There's many, many challenges, but I think I'm just going to illustrate one, and I think it's representative of the challenge that we face. So these are IBR-driven oscillations. So that diagram down on the bottom right is real data from Great Britain, okay? And what it is it's kilovolts and time, and The panel on the right is a zoom in of the panel on the left. And what's going on is that there is this weird oscillation that happens around 400,000 volts, going up to around 430 and down to 360. And it's happening over a period of, what, a couple of minutes? 45, yeah, in fact, 10 seconds, 20 seconds. So it's a very small burst of oscillations. If you have an oscillation of 30, it says there plus or minus 8% per unit, almost 10% variation, completely out of nowhere. Like no one knew it was coming. No one knows why it happened. So I'm being a bit provocative here. They did not know it was going to happen. When it happened, they didn't know what caused it, and they still don't really understand what caused it. You cannot run a power system like that, because this event, for example, not this one, but several of them, for example, have tripped off a nuclear power station. So these events, if they keep happening, will undermine the reliability of the power system. And they are completely we're absolutely certain it's because of these inverters. Because the synchronous machine is a physical lump of metal, and it has certain characteristics. The inverters are a piece of silicon and has software. And they're two entirely different beasts, and how they behave is totally different. These oscillations are caused by the inverters. And I've put in Texas and Australia. They're happening everywhere. Yeah, they're happening in Great Britain, they're happening in Texas, they're happening in California, they're happening in Australia, they're happening in Ireland. All the places that have lots and lots of inverters are starting to see more and more of these. And I mean, the scenario I give you is that there's a blackout. I won't speak about blackouts in Texas. It's not a good thing to do. But to say there's a blackout in Great Britain, say the UK goes black, the CEO of National Grid, or NESO, which is the new system operator in the UK, National Energy System Operator, just formed this summer. The CEO is one of my students, and he's sitting in front of the select committee or whatever in Parliament, and they say, "So, Mr. Sly, what happened?" And he says, "Well, got a wobble, tripped everything out, blackout." Why did it happen? Sorry, no idea why. What are you going to do about it? Well, until I know why, I can do nothing. So whether he loses his job or not is up for debate. But nonetheless, that's not a good scenario. Okay, I'm being a bit provocative. It's not quite as extreme as that. He definitely will be able to identify certain things and all the rest of it. So that's an example of the IBR challenge. And it's not in the future. It's here now. And that's one of the things about this area, is that an awful lot of the research that people like me are doing, like when I started this area, we were looking at future scenarios 10 years out. We're now working with the system operators on a day-to-day basis, trying to solve the problems they see now, because they are research problems, but they're research problems that we should have solved 5 years ago. So we're actually working. So people say it's very applied. It's very applied because it has to be. So the timeline between the research that we're doing and the application is no longer, there's no distance between it. We're actually working directly with them on it. Just to sort of put that in context again, a little bit more from my own point of view from Ireland, this is a slide from Ireland. We have the same problems in Ireland. To be clear, I'm not saying this oscillation issue that's happening is illustrative of many issues that can happen, but there are other ones as well. So for example, in Ireland, because of the inverters again, we used to have a strict limit of the amount of wind that we had on the system to 50%. It was called the SNSP, the synchronous non-synchronous penetration level. We used to limit it to 50%. But then we did all the research work and we got up to 75%. And this illustrates it. So operational limits are on January 12, 2023. And if you look at it, you can see that the wind and the wind and the load almost follow each other. And that's actually untrue. What's happening is the wind wants to go even higher, but it's been curtailed. And if you have something that wants to go higher and it's curtailed, it tracks it. So in fact, the optical illusion that looks like the wind is following the load is actually this constraint. Okay, so we're implementing now. We've gone from 50% to 75% with research, and just to illustrate it, that bit in the red, that's the bit we don't know how to get to, and that's again the research that we're doing. Just to put that in context, what that means though, so you can get rid of these things by curtailing the wind and solar, but if you curtail it, what happens? Well, costs go up. Yeah. You're throwing away incrementally free energy and having to replace it with incrementally not free energy, and therefore the costs go through the roof. So the economics is becoming, so this trade-off between reliability and cost is real. If I want to get reliability in these situations, I have to curtail, I have to increase the cost. So that trade-off is happening for real. And this illustrates, and this is a simulation and some study, that as the SNSP goes towards 100%, where these are no longer constraints, we get far less curtailment. You get curtailment for other reasons as well. But you can see if we don't curtail it, what will happen is the costs go through the roof. So it's a cost issue. So look, I could go on and sort of dig deeper into that. And in fact, one of my PhD students has his ESA on Monday, which is the early stage assessment that Costas knows, or that Stratus knows all about in Imperial. And this is a draft of a paper. And I just thought I'd throw this up for fun here. I could start going through how we got all those, I don't know, 24 graphs and spend from now till lunchtime doing it, but I won't. This is a problem that power systems and power electronics people have to solve, and we're working on it. So I'll leave that. I want to talk about the balancing challenge, which is a broader challenge, which involves more people than just electrical engineers. This is from this paper in Joule by Paul Denholm from NREL. He shows it very nicely that the real problem is the seasonal challenge, right? So this is the case. We all know the situation when the wind don't blow and the sun don't shine, the usual thing and all the rest of it. So this becomes, if you want to go to 100%, I'm not saying you should, I'm simply saying if you wanted to, what happens? And this is what research is about, is testing those boundaries to see what happens. So if you wanted to go to very high penetrations, and like if things don't stop the way they are, if people keep putting on wind and solar, that's where you will go, okay? Provided the economics are right. So the real problem is seasonal. It's not day-to-day, hour-to-hour balance, and that's easy. It's done. It's all, we know how to do it. So it's a seasonal challenge. And the best way I can illustrate it is, and if you look at YouTube and find me giving lectures, I've used this slide more than nearly any other slide, and I keep on threatening to update it, and I never do because it suits. So this is just, I have updated today. I did a special job for you guys. So this is a very simple but very illustrative sort of diagram. What it shows you is it's the load in Ireland. It's 2010 load as well, so it's a bit dated. So the slide is 15 years old, but like I said, it works, so I'll just keep using it. So it shows you the wind, it shows you the load in 2010 on a monthly basis, okay? And I'll talk about in a minute when you go to weekly and hourly resolution, you get different things happening. I'll address that. So if you look at it, it just says monthly load in Ireland is in blue. And then we took the wind in Ireland in 2010, which is pretty small, and we said multiply it up so as the area under the curve is the same. In other words, I have the same amount of energy from wind as I need, okay? Simple experiment. So we scale up the wind. So the wind is there and it's got a monthly profile and it's scaled up so as the area under the two curves is the same. That's in red. Now you can clearly see in Ireland that it's windier in the winter than the summer. That's basically what it's telling you, okay? And it's at a monthly resolution. And it says to you, well, the bit in yellow then that's the bit that's missing during the summer, and that will also equal the area under the curve that's excess during the winter. And the question is, well, could I store it during the winter and wait till the summer? That's the seasonal storage challenge, okay? Now, the answer is, of course you can do it. The technology's there, like someone said. But just to put some numbers on this, right? That's my electric vehicle. The white one, and on it is my notebook. I don't know why my notebook's on it, but it is. That's actually in a car park in Kerry, in the west of Ireland. And I was giving some talk the following day, and I was doing it on my notebook, and I quickly jumped out of my car, took a picture, and then went back into the car and put it into the slides. That's an Ionic 5. It's a 75 kilowatt hour battery. You would need 37 million of those to fill that gap. Yeah? I mean, 37 million EVs. Ireland, we have around about, I don't know, we might have 700,000. I know, we might have 1 million cars, I'm not sure. But what you're talking about is not electrifying every car. You're talking about electrifying every car and buying 40 times more. So it's insane, okay? If you go then, we do have, the next picture shows you 2 lakes. It's a pump storage station in Ireland. And we have 1 pump storage station in Ireland. And if you could build more, and you actually can't because the sites are not there, but nonetheless, if you could, you'd need 1,560 of them. And remember, I have not taken into account anything to do with losses, etc. I've said I can store it and get it back for free. Not going to happen because of the second law of thermodynamics. So this is generous at the very soon. 1,560 terlakils, yeah, at a cost of roughly $1.8 billion each, for an island system that has 5.5 million people. Like, it's insane money. But I think the best one of all is the AAA battery. 3 trillion. Now, I don't know the numbers. I'm sure the chemical engineers can do them or someone can do them. I would suspect we have not or will not make 3 trillion AAA batteries ever. I would suspect, but I'm not sure. Okay. But it just puts it into scale. You're not going to solve this with batteries. Okay. Everyone agree? Not going to happen. Now, just to be clear though, that's a monthly, it's averaged over monthly. And if you go down to weekly and hourly, you'll see slightly different things. But in general, the point is still valid. So this shows you some results that Paul Denholm produced. He looked at ERCOT and he looked at California. He went to 100% various scenarios. You can check the paper out and see exactly how he got it. But just to point out that what it shows you that on a more time resolution basis, you still have the same problem. Okay, there are places. Just one page of pointer here. There are places here, for example, where a bit of sort of daily storage will help. So there's no doubt about it. If you go down to lower time resolutions, there are places where daily storage helps, and this is not as bad as it looks. But largely speaking, it stays. There is a seasonal challenge, and if you do it everywhere in the world, it's largely speaking the same. Now, it's different. Sorry, it's the same basic concept. It's different in nature, in that some places, the seasons will be different. Like we're a winter peaking system, you're a summer peaking system. There's different variations, but no matter what you do, the simple fact of the matter is large-scale storage is required. And that's it. And, if someone says to me, well, what about if you mix wind and solar together? And the answer there is yes, that helps, because with wind only, it's correlated. But if you put in something that's anti-correlated, it helps again. And this shows you results that, yes, things improve with wind and solar. But again, just to go back to this graph here, this is 45% PV for, Paul Denholm did the numbers on the combinations and all sorts of combinations, permutations thereof. So basically, you can take it from me. The season storage challenge is there. It's pretty much there everywhere. It's a real problem. So now, I'm now into the league where I don't know what I'm talking about. And therefore, I can say anything I want. So hydrogen. And I had a call, Leverhulme, so I don't know, Leverhulme organized a call with some of my colleagues in the room. We're going to have a panel later on, and pretty much they're all hydrogen people. So I want to be very careful, I suppose. I could get lynched at the panel session. But anyway, so Michael Liebrick is, I don't know if you know him, he was the founder of Bloomberg New Energy Finance. He's in London. I know Michael pretty well. And Michael's a bit of a talker, I'd have to say. He's a good talker, and he puts out stuff. And he created this thing. He called it the hydrogen ladder. And if you look at it very carefully, what it shows you is if you take hydrogen and if you take, so he's got so no real alternative. Electricity and batteries are competitors, biomass and other are competitors. So he tries to color code them, and then he tries to do them competitively. So basically he's saying is what's at the top, hydrogen starts to become competitive. As you go down, it becomes less competitive. And then he shows you in color code what are the alternatives. For example, with the one that's going to become relevant later, steel. Electricity there is an electricity option for steel if you wanted to use it, hydrogen or steel. So I think it's very useful. But look at bottom right-hand corner, last place is that. So what I'm asking the question is, why are we spending all this money on hydrogen research? So I'll just put it out there, it just seems to me, from what I see from this is that, and I know that Michael Lee, because I know a very good friend of Michael's as well, I won't say who he is, but I had lunch with him in London. He's an investment banker. And he says, Michael has learned his lesson from hydrogen because he invested and lost. So he, being objective about things, when you invest in something and lose it, you tend to be very objective afterwards. Anyway, I'm not damning hydrogen. Well, I probably am, but what I'm saying is I don't think for this partisan balancing it's an option at all, right? I just don't think it'll happen. So we have to find something, and there's nothing else. Well, there's other things out there, I suppose. No, sorry, and to be absolutely clear, there are other things out there, nuclear, CCS. So, the scope of this talk, I have to keep it pretty limited. I'm sort of saying, just if you went down this road of lots of renewables and storage as an option, there are other options, and we could go there, we could talk about them, but let's just keep a bit focused. So I'm a Hagler fellow at Texas A&M, and Leverhulme, where's Leverhulme? Leverhulme's branding is all over the place. I found this in the middle of the campus, and it says Supply Chains and Analytics course this way. So supply chains. So when I came to Texas A&M and went down to the Energy Institute, and I met Stratus and Leverhulme, etc., and Leverhulme into supply chains, A lot of people have said that this problem of balancing can always be done by demand side management. But I've just shown you, what are you going to do? Are you going to charge up your 37 million? Well, you have 40 times too many cars to start with. Are you going to charge them up in the winter? And you're not. So small loads don't do anything for this. So I've always been a very big skeptic of demand side management. It works in certain places. It is competitive on the short-term basis, but it's a niche. But yet, what do? We produce enormous numbers of papers on it. And why, I don't know, because it's not really going to be a solution. Not for the real problem. They're avoiding the real problem. The real problem is seasonal. But one of the things is, if you look at, everyone says, well, we got to look at big loads. So that's fair enough, So we go to the steel industry, the cement industry, and we say to them, can you be flexible? And the answer, generally speaking, is we can be a little bit flexible, but only on a daily basis. And it still doesn't address the problem. But if you think about it, and this is what I learned when I was here from the supply chain people, is that the reason they're not flexible is because they're in a supply chain they're in a supply chain, and the way the supply chain is designed, they are 24/7, 365 days a year. But if you put physical storage in along the supply chain, you may not have to run them 365 days a year, 24/7, and therefore they will become flexible. But there's an extra cost of storing goods, and there's probably an extra cost in terms of the capacity of production, etc. So you can store goods, and then you have to pay a little bit extra. But the question is storing the good and paying a little bit extra, will that solve the problem? And here's the other question. Is it cheaper than going to hydrogen? And I'm telling you here and now, as far as I'm concerned, it is going to be cheaper than hydrogen, because and also it's more certain. Why? There's no fundamental scientific breakthrough required. There is an organizational thing. Society must reorganize itself. Industry must reorganize itself. But we don't need fundamental breakthroughs in science. And we certainly don't. Well, in hydrogen's case, I think we have to actually break the second law of thermodynamics to make it work. That's never going to happen. So the concept was born that, supply chains and VRE are dance partners. They fit well together, okay? So supply chains have a volume of energy that's relevant to the problem at hand, because a lot of people look at demand side management and you suddenly realize, yeah, so what? You're going to turn off my air handler. It's, the volumes are just not there. So a lot of people are attempting to do what I call, they're attempting milliwatt hour solutions to terawatt hour problems, yeah? So here, the cement industry, steel industry, they use lots of energy. So from a volume point of view, it's there. The cost of energy, I would guarantee that this is almost certainly 100% correct. I'm sure someone can find an outlier. The cost of energy storage is way, way, way less than the cost of... Oh, sorry, I've put the arrows the wrong way, haven't I? Pardon me. Yeah, I've just noticed that. So, but the cost of storing products is way, way cheaper than storing energy. I think that's a given. I think I can make that assumption. Like dramatically cheaper, yeah? You get some products and just lay them out in the turf and that's it. That they're stored. So much cheaper. Supply chains are diverse. Yeah, in other words, they're not, there's different supply chains, and diversity is very important this area. I showed you the diversity of mixing wind and solar, but diversity is very important. So they have diversity, steel, cement, they're just diverse, right? And flexibility in supply chain should also improve the resilience of supply chains. Now, I have put resilience in inverted commas because to electrical engineers, resilience is not the same as what Leverhulme means. So we'll have a fight about that later. But, we use the term resilience, we use it slightly differently. But nonetheless, resilience of supply. If you build storage into a supply chain and there's some disruption in it, you have storage. So I think there's an added benefit here to the supply chains. They themselves become more resilient because they have the storage, but they also have the benefit that they're probably able to use very cheap renewable energy. So there looks like there could be a cost benefit trade-off and resilience benefit. So it looks like there's plenty of stuff on the upside. So if paired with variable renewable energy, supply chains can benefit from zero. Now I've put inverted commas zero cost. They're not zero cost, of course. They're zero cost operationally at that time because no one wants it. So from a point of view of the manufacturer, it's free. Yeah, because it's zero cost. I'm not for 1 minute saying zero, but that's what people see, zero cost. And you reduce emissions as well. Okay, so there's sort of the benefits. Now, there's a very good quote here at the bottom. VRE enhanced grid can assist 1, energy efficiency, 3, emissions, and 2, supporting resilience for supply chains and grid that will increase the strain, data centers for cloud AI, and huge contributors to this. So who's that quote from? Very famous person? Leverhulme. He sent me an email this morning, a long email about, and he says, he looked at my slides, and I said, to hell with him. I'll just take out that sentence and put it in, and I've dealt with it. So I've dealt with your comments, haven't I? Done. So I want to remind you of this diagram. We could put supply chains into this diagram, couldn't we? Yeah? So they're integrated. So the whole thing of VSI is integrated together. So some numbers. So this is work that we've only started recently, and the numbers are, we do have numbers, and we're not here to give you, I'm not going to give you any numbers that I'm going to stand over. I'm not going to say that these are correct. I'm simply doing some illustrations, because to do this properly, you have to do it very rigorously, very carefully. And we're in that process at the moment with Aman, Elnaz, Lifteris, Halil, and then some people in Georgia Tech, Chip and Constant. So we're working on it. So this is sort of pre-data, if you know what I mean. Don't go quoting me, right? But it just illustrates some of the things. NREL has a data set that they looked to the future. They split the US into many regions. I think there's around 13 regions there. And they did some projections of what the price of electricity will be in certain future scenarios, okay? Now, there's simulations, and you have to go into the simulations and see the assumptions, but bear with me for a minute. Just this is the data that we have. And if you look at the data, if you look at this again, what you're trying to do basically is you're saying, to solve this problem, what you need to do is you need to basically say, can I manufacture during the times of low price and not manufacture during the times of high price, basically? So can I make the supply chain flexible? Now, I absolutely understand there's other things here as well about labor. The workforce becomes seasonal, but you have seasonal workforces, don't you? We have it already, so it's not a case you don't have it. So there's all sorts of other issues, so we're not underestimating them. And the proxy for that is the price, okay? So if you look at 2030, average weekly price comparison, this is from these simulations. They've taken the US, they've put in 56% electricity comes from wind, solar, and hydro as a scenario. And they've done some prices. Now, it's a little bit, we do have all the regions, but I asked Elnaz to just give me the most variable, the least variable, and Texas, yeah? Obviously, you have to do Texas. You're in Texas, you have to do it. So if you can see from that, you can see that the weekly prices in 2030, there's a huge spike in prices in California, yeah? So California definitely has a seasonal pattern, doesn't it? Very expensive in the summer, cheaper in the winter. ERCOT also has a similar pattern. It's a little bit shifted towards the spring, but it's still there, but it's not as high. SPP, virtually no pattern. What that immediately tells you, if you're going to try this, and if this scenario is correct, SPP is not the place to do it in. Texas might be the place to do it in, but California looks like it could be the place to do it in. So it just gives you an indication where it's possible. If you go to 2050, now just be careful here. The scales, the axis on the left is 300. Axis on the left here is 600. Things have got far more dramatic. We should have really done them on the same scale to show it. But basically, what's happened here, the California price spread is enormous. The Texas price spread is still there, but in fact, it's lower. You'll see in the next comments, it's actually declined, and SPPs have stayed bad. So let's go on and do that in another way. Same data, just looking at a different way, 2030. Now what we did is we just took the fall, spring, summer, and winter, took the average prices, okay? Now in 2030, you can see it a bit clearer, right? There is a big average price swing between the summer and all other seasons in California, and it amounts to, what, $50 on average, yeah? So if you tell someone there's a $50 premium to be got here by manufacturer at a different time of year, and if you're using enough energy, the numbers, might start to add up. But if someone tried to do it in Texas, the price spread might only be 40. So it's probable that, but it depends on the product. It depends on all sorts of things. And it also depends on the demand for the product. The demand for the product could be seasonal. So you have to take, there's lots of other things. Before you can say it in concrete, there's lots of other numbers to be done. So I'm just simply making an illustration. But if you go to 2050, you can see, interesting, ERCOT has got worse. In other words, it's not as volatile. Now that has to do with the scenario. So you have to look and see what that means. So I'm not saying this always happens with more renewables. I'm saying it's happened sometimes. But for California, the average price spread now has gone to well over $100, yeah, seasonally. And in ERCOT, it's only down to 30. So you have to be very careful here. It makes a very important point about this. Every case is different. But I think that this diagram here says, if there's a $100 premium winter to summer in California, and if you can be guaranteed, that makes a good business case to maybe shift my manufacturing seasonally. But that means I have to change the entire supply chain, so it's a non-trivial problem. But like I think John Junkin said it very well, we're here to think outside the box and think big. I think this is pretty big. So what we're doing at the moment, just to give you, now this work is ongoing. We're looking at the supply chain for steel. This is steel, and you can see it's electrified, and that's one of the reasons I pointed out steel has been electrified. It's a competitor for hydrogen. So we're modeling the actual processes themselves, right? Because to really justify this, you have to go right down to the detail. You can't just show the prices. You have to show, well, what's the actual profile of energy use, etc. So we're doing that, and then we're also doing this. We're taking different supply chains, and we're actually modeling entire supply chains, and we're putting the grid in. So this will take a lot of time, a lot of effort, a lot of data needed to do correctly, and hopefully in the next couple of months we'll have some much better preliminary results that we can publish. But I think to really justify this is going to take several years of really hard work. But if you can come up with a business case to someone in the industry and say, look, here's the business case, here's the savings, here's the benefits, and if you justify it, maybe industry will shift. Just on another, so we're working, so at Texas A&M, this is the work that's been done, and our colleagues in Georgia Tech are doing a little bit of a slant on this, where transport is the key. They're transporting things with electric vehicles, so there's more of a transport flavor in it, but it's the same basic concept. And I want to show you this. This is a simulation, so this should start to simulate. Just to be clear about it, the no carbon tax and the $50 carbon tax, don't read that into it, what it looks like. It's simply a proxy for the fact that we did not take into account any economics. And basically, you can basically take it from me that they are comparable in cost terms, right? What we simply did is we penalized fossil fuels against renewables, not because we're penalizing them economically, because we wanted to make sure that we were putting them into the system. So it's a proxy, so don't. I was trying to take it out this morning, and I said, if I take it out, I'm scientifically not correct. It's not as it looks. And besides, these are illustrative. So here you go. So this shows you on the left that in a transport sense, there's the base case, right? And you can see this is transport, right? And there's inventory. I can't remember what product. Chip, what product is this? What product is this? Not sure. So I've asked the supply chain expert. He's not sure. That means I can be not sure too. But the simple fact of the matter is, what you see is that if you take the concept I started with and apply it, what happens is the transport changes, which means that the supply chain is changing. And these results are a little bit more rigorous, but still we're not there at a point where I can sort of give you all the methodology, whatever. So I'm being very careful. These are sort of illustrative.
Commodities, Mark, right? So it's,
Sorry?
It's commodities that cost us more.
Yeah.
Supply chain for commodities.
Okay, how am I doing at time? Perfect. Yeah. No, I'm on time. I'm a Hagler fellow. That's we're always on time, John, isn't it?
You can talk as much as you want, Mark. Yes.
His wife said to me when I came in here yesterday, she was expecting me in my flip-flops, which shows you the extent of my wardrobe. I won't go. I mean, this is another more results, but they're a bit difficult. So the last thing I want to talk about, actually, believe it or not, is the stuff that I'm interested in. I mean, sorry, I'm obviously interested in lots of things, you can see. But I'm mainly interested in my Leverhulme Trust grant, the big grant that brought me to Imperial. It's needs and services. Where I sit most comfortably is somewhere between electricity markets and power system operation and planning. I sit in between the two, okay? So needs and services, the power system, energy is the main service that most people know, but there's other very technical services. We call them ancillary services, whatever you want. There's these very technical things that unless we have the reliability of the system, doesn't happen. Now, again, they're mainly in the sort of the realm of electrical engineers. It's not, this is not for the faint-hearted, if you know what I mean. This is electrical power. Like this is, I know that Chip, Chip doesn't know this. I know that Chip was quizzing up Constance, who's a friend of mine who works for him. Or worked with him in Georgia Tech, and she's working this. I know that he was quizzing her up about what is reactive power. So you have to understand reactive power, power system dynamics, electromagnetic. It's our business. Stay out of it. We know what it is. But if we don't have them, the system collapses. It's that simple. So they're incredibly important. So I pitched a research program in Imperial around systems and services. So I think the single best diagram, and I only need one diagram to do it, so I'm not going to go too much detail. And I think it illustrates a sort of a final sort of point to be made. If you look at needs and services, which essentially, and sorry, let me go back here. Sorry, let me go back here. So energy and capacity, the main service that people want is energy, let's say. Capacity is a technical thing as well, but on the right are these technical services. They're the things that us electrical engineers know about, okay? So you need them. So you think about them, they're here. There they are there, you need them. This is the power system. That's the electricity grid. But you have all this other stuff out here, which is the rest of society. So you have the political economy. So somewhere in there, the governor or the politicians, they decide on the level of reliability. Remember I said some level of reliability to be defined? Well, society decides that. I want more reliable grid or whatever. So that's the sort of what and they might also, to the objective, maintain reliable supply at each cost. But they might come in and say, well, for some reasons, we want to encourage the nuclear industry in Texas. So, build nuclear. So there's all sorts of, let's be clear about it. Is there such a thing as a free market? You must be joking. Governments always interfere. So you've got some sort of, line item there that influences things. But down below, you have the manufacturers, entrepreneurs, and all the rest of it. And they make investment decisions. And then there's technology innovation. But at the end of the day, they're all driven by the services because that's what pays them money. So in terms of the evolution of the market and what happens from a competitor, to Ryan's point, you have to get the needs and services right. Because if they're correct, right, at the center of it, the innovator or the manufacturer can all see my product, device, whatever it is, that's the money pot I'm after. And they go after it. And that's what will motivate them. So needs and services are incredibly important to get right. One sort of very, very, and on that sort of side, I better put in a negative here somewhere. I better sort of deflate my own bubble here. Be very careful though. Storage kills its own market. If something like this starts to happen and if cement manufacturing goes seasonal, the load starts shifting and all of a sudden the price starts to rebalance. So there is a new equilibrium of some description. So this is not all, you have to be very careful here. So that's just a word of warning. There's many others I can make, but that's one of them. So the conclusions. Do you know more or less than when I started? Hands up. I couldn't lose in that, could I? Anyone totally confused? Well, there you go, that's good. John, value for money. Speaking of value for money, just as a sideline here, John Sharp has tried to hire me twice. Both times he offered me an oil well, so he's right, we're not cheap. But we're a lot cheaper than football coaches. And remember, they didn't perform. But anyway, let's not go there. That's a different. I wouldn't rub salt into the wound there. Okay, so nobody knows the answer to the future energy system. Anyone who says they do is lying. Okay, some of the challenges do sit well-defined disciplines. So I've made a point that in some of these things, there's no point in me talking to you guys about power system stability, reactive power, dynamics, power electronics, grid forming this, system strength that, protection this. It's all electrical engineering, and that's where it should stay. Yeah, we want to keep that there because it helps our consultancy rates very high, so we'll keep it there. Most challenges sit across the disciplines, though. Most of the real challenges sit across the disciplines. And then on the specifics, so leveraging the flexibility in the supply. I'm sorry, the elephant. You know what the elephant is, the famous one where all the blind men are feeling the parts of the animal, but nobody sees the whole animal. So that's the analogy there, okay? That's the sort of, nobody knows everything. The iceberg is to show you that you only see part of the problem as well. I think it's very important because what I've shown you is the top of the iceberg, but down at the bottom there is probably the stuff around labor. There's other things, there's lots of other things that are out there. But if you don't get the physics right, nothing else works. So leveraging flexibility in supply chains appears to have some validity, yeah? So I've been very careful with my wording there, yeah? To date, results are only partially known on a the case-by-case basis is the thing that concerns me. I think we could do a really detailed analysis and show it for one thing, but it's very, can you make any generic statements is a very important thing. So that's what I think what we really should try and do is generalize this in some way. But only time, good analysis and careful consideration of the competition. And I think that's really important. Back to Ryan's point. There's no point in solving a problem when the competition can do it cheaper and faster than you can. You must always keep your eye on the competition. And I'm keeping my eye on the hydrogen business, and I'm keeping my eye on the amount of research money that's going into it, and say, why can't we have a piece of that? That's my competition. So lastly, I'm afraid my ego got the run of me, and you can blame Stratus for this. He said, I want you to end on an electrical engineering note. So I hate to rub it in. So the greatest engineering achievement of the 20th century was electrification, according to the National Academy. My belief is it'll be the greatest engineering achievement of the 21st century. It'll be at the center of an energy system. So I think the electrical engineers win out in the end. Thank you very much. Oh, sorry. So I've lots of people to thank, obviously, and I did it by picture. So top picture there is Lefteris, Elnaz, Halil, and Eman. And Chip, I don't have a picture of you, so you didn't make it into the lineup. But this lady here in the front here, that's Constance from Georgia Tech, and all these are other people that I work with around the world. That's it. Thank you very much.